All right, it's 11:15. I think we'll get started. So welcome back. It looks like we have a reasonably full class. So most of you made it through whatever weird spring snow we just had. We used to have that same snow in May where I went to school. So you're lucky to only have it in March in Pennsylvania rather than in Upper Michigan where we get our last blizzard in May. But anyway, any questions or comments before we get started? Yes.
Before we make the PL line, I'm not really sure if I'm allowed to really ask it, but what's the difference between the confirmation between the bond and the bond?
That's a good question. So the question is, what's the difference between a confirmation in a bond versus confirmation in a molecule? Because the PLA, you know where we're headed, and we have a couple more topics to cover before the exam, which is next Wednesday. So we have a regular week this week, homework, PLAs, all that stuff. And then we'll have exam review on Monday and exam on Wednesday next week, just so we're all on the same page. And you can check the PDF syllabus dates if you have any questions. So the confirmation of a carbon-carbon bond, what did you learn in organic chemistry? What are those confirmations called? When you look at the Newman projection and you look at down the carbon-carbon bond and you twist the methyl groups, what are those confirmations called? Yes. Eclipsed, gauche, trans, cis conformations, things like that. So for a bond, the confirmation is we're talking about the rotation around that bond, like you're looking right down the carbon-carbon bond, like in a Newman projection. The confirmation of a molecule is, we can say a molecule is all trans, or we could say it's planar zigzag, or we can say it's extended conformation, it's stretched out, or we can say it's globule. And so sometimes molecular conformations have a few different types of ways to describe how a long polymer molecule, which is a bunch of carbon-carbon bonds, is all coiled up, or is the sum of all the conformations of the single carbon-carbon bonds. And so you should remember the single carbon-carbon bond conformations from organic chemistry, and we're going to put the polymer conformations on top of that. Does that make sense?
Sure.
Okay. Yeah, check out the PLA. Remember, I didn't make the PLA due yesterday because yesterday was still officially spring break. The PLA is due tonight, and so make sure you take a look at it, and that's where we're headed on Wednesday and Friday. Any other questions? All right, good. So we're just going to finish up copolymers. I think this is the last lecture. We'll talk about copolymers. And remember what the situation is. We have a mixture of monomers. So we talk about this vat that we're going to make a polymer in. We have a mixture of monomers, and we're going to describe that mixture by some sort of mole fraction, which is small fa and small fb, right? Then we're going to make polymers out of that, and we're going to make chain growth polymers. And so we're going to make polymers quickly as a function of conversion. And so what we're talking about is how to figure out the order of these two monomers in the polymer chain. And this is an okay representation of this problem, that we start off, and if the reactivity ratio, so this is a 50-50 mixture of orange and blue monomers, I think. And if the orange monomer has a higher reactivity ratio, we're going to incorporate orange in the chain first, right? We can tell that from the diagram. But then we run out of orange. And so even though orange might have a higher reactivity ratio, we only have blue left. And so blue has to come in at the end because there's no orange left. And so remember, the copolymer composition is both a function of the mole fraction of monomers that you have, or what monomers are available, and the reactivity ratio. And we'll emphasize that today. And like I said, this is an okay representation of this problem. And what do we call this, where we have a different composition at the beginning of the polymerization versus at the end of the polymerization? What's that vocab word? I know you're all thinking about it last week. It's a big word. Compositional drift. right? So as the mole fraction of monomer changes, as our small FA and small FB change, the composition of the polymer changes, and that's called compositional drift. And so that's why, in general, we talk about running these polymers at low conversion or for a small conversion so FA and FB don't change. A better representation of this is that, let's say this is our chain growth curve. You should know that by heart now. And so let's say that FA is greater than 1 and FB is less than 1. So in general, the polymer is going to be enriched in A, right? And so as a function of conversion, in a small slice here, this polymer will be enriched in A. And let's say, oh, I'm sorry, I need to come back from spring break too. RA is greater than 1 and RB is less than 1. And FA equals 0.5 and FB equals 0.5. There we go. So we're going to be enriched in A there. But if we go to higher conversion, so say we have this situation, that's what we put in our pot, 50-50 monomer. We run the polymerization for a while, or we run to higher conversion. What's happening to small FA as we make more and more polymer? FA is doing what? It's decreasing because the polymer is enriched in A, which is FA, right? So you're taking monomer A out of solution and putting it in a polymer, even though the polymer is in solution too, but you're lowering FA. So FA goes down. So let's say FA goes down to 0.3. What is FB? Yeah, 0.7. They have to add to 1. So no matter how much monomer you have, we're talking mole fractions. So they have to add to 1. You just need to know one mole fraction, and you get the other. Now, we would have to run the Excel sheet, and we'll do this in a sec. But let's say FA equals 0.3 and FB equals 0.7. Have RA and RB changed as far as we know? No, those are set. Reactivity ratios are set by the chemistry. They're set by the monomers. They don't change with conversion. But has the copolymer changed now? So say we want to know the copolymer composition at this conversion. We've run the polymerization. Has the copolymer composition changed from where we started? At FA equals 0.5, FB equals 0.5. And the answer is yes, because the copolymer composition is determined both by the reactivity ratio and by the mole fraction of monomers. Now, RA is still greater than 1 and RB is less than 1. And so this polymer will be enriched in A, but it will have less A than this polymer. Let's call this polymer 1, polymer 2. So polymer 2 has lower FA than polymer 1 because small FA has gone down. So in our spreadsheet, we're calculating things over all compositions of small FA or all mole fractions of small FA. And we're really focusing on what happens with the reactivity ratios. Don't forget about what happens to the mole fraction of monomers as the polymerization goes on. And this is called compositional drift. And we'll continue to emphasize that. So, any questions or comments so far? Yes.
So if we start enriched in A, no matter how we change FA and FB, we're always going to be enriched? in
That-
A?
That is a very good question. Let's go to the spreadsheet and find out, right? And so if we go to our spreadsheet, well, and I have it backwards here. So RA, I said, is greater than 1. So let's go 4. And RB is less than 1. Doesn't matter what it is, 0.5. Whoop. So this tells us no matter what, because the blue line is above the 45-degree orange line, no matter what FA we pick, sorry, FA is right here, we're always enriched in A because capital FA is above the 45-degree line, which means capital FA is larger than FB. So when we have this situation, that's always true. So when RA is greater than 1 and RB is less than 1, it will always, the polymer will always be enriched in A no matter what the composition is. So if you look here, when FA is 0.1, so we have 10%, 10 mole percent A and 90 mole percent B, we still get a higher FA than we expect, right? Than the 45-degree line. And that comes right from the copolymer equation. So making this spreadsheet and testing it and understanding how these curves come about is important. What is the one exception where we can go from a polymer that's rich in A to a polymer that's poor in A, depending on the mole fraction of monomer that we start with? What do we call that special case? So in some cases, you would have a polymer that's rich in A, and in some cases, you'd have a polymer that's poor in A. And so you have to, the blue line has to do what? Cross. And what do we call that type of polymerization where the blue line crosses? Azeotropic polymerization. And that occurs when we have reactivity ratios that are both greater than 1 or both less than 1. So under azeotropic polymerizations, we usually focus on this point. So we usually focus on the azeotrope. And so in this case, that looks like about 0.2. So when we feed monomer mole fraction small FA of 20% or 0.2, we get the exact same capital FA in the polymer. Does small FA change under these conditions if we're sitting at the azeotrope? No. So when we're on the 45-degree line and we have the same mole fraction of monomer that's going in the polymer, there's no change in small FA with conversion. That's very interesting because we can run the polymerization as a function of conversion, and we get the same composition no matter what the conversion is. I won't write that down here, but that's something that you should think about very carefully. Well, let me write it down for you. 4 points. On the 45-degree line, small FA equals big FA, no change in FA with increased conversion, and this equals no compositional drift, or formally no change in FA with conversion. That's an important concept. So for an azeotropic polymerization, if in this case, if you have small FA of 0.1, is the polymer enriched in B or in A at this point? It's enriched in B because we're below the 45-degree line. And so if we go up here, 0.1, capital FA is 0.05, which means the polymer has more B in it than we expect, or less A in it. But if we increase FA, say if we put FA of 0.5, all of a sudden now we're getting a capital FA of 0.6, so the polymer is enriched in A. So azeotropic, it really matters. It switches from enriched in B to enriched in A. And of course, at this point, the composition is the same as the feed. And so we have to remember that azeotropic case. And if we just do the opposite azeotrope or the inverse azeotrope, let's do 0.3 and 0.1. There's our azeotrope, and it switches the other way. So that's an interesting thing to think about. What happens during azeotropic polymerizations versus what happens in your garden variety polymerizations where, let's say, A is 0.3 and B is 10 or whatever. Great. And so having this spreadsheet, thinking about it, messing around with it, thinking about what happens when you change FA, thinking about what happens when you change reactivity ratios. You know, there's not going to be tons of plug and chug on the exam. There's going to be a few plug and chug questions, but also some conceptual questions. So we're going to practice that in the clicker questions today. All right. Any questions so far? Any comments? All right. So the key to all of this is remembering the fundamental reaction. What are these 4 reactions? Why are they important? What do the Ks mean? And how do we go from Ks to reactivity ratios? So when in doubt, make sure you look at these reactions, make sure you look at the Ks, make sure you think about what the reactivity ratios mean, and then it's much easier to answer these questions. All right, where are we? Talked about all that, talked about all that. Talked about compositional drift. All right, so clicker question, you can get out, and we're at C and D in this room. Make sure we all made it back from spring break. All right, so the conceptual questions will be asked like this. So if RA is greater than 1, and RB is less than 1. Okay, I think about what that means. I'm going to be enriched in A for all compositions. Then FA does what? Increases with higher extensive reaction, decreases with higher extensive reaction, or does not change as a function of extent of reaction. And you know that extent of reaction, I'll go back and forth depending on the source, extent of reaction is the same as conversion. So you don't need a plot to help you answer this. You can think about, okay, RA is greater than 1. And so what do I know when RA is greater than 1 and RB is less than 1? What's happening to monomer A? Polymer is enriched in A. Okay, if the polymer is enriched in A, what's going to happen? Small FA is going to increase with higher extensive reaction. That's not a very good answer. Does not change as a function of extent of reaction. That's not a very good answer. And so I'm only left with B, decreases with higher extensive reaction, just like we talked about. And this leads to compositional drift at high extents of reaction. Now, if we just do low extensive reaction. So that's why it's phrased in some of the problems at low conversion or low extensive reaction. We're only working with one FA, 0.5, and one capital FA. So if we have low conversion, small FA doesn't change. And so we're only talking about one composition of polymer, and there's no compositional drift at small extensive conversion. If we are at this point right here and we go to large extensive conversion, then we get compositional drift. And so you need to make sure, are we talking about just a small incremental conversion or low extensive reaction, or are we talking about big extensive reaction? All right, up 50, that's good enough. All right, and so there's some ways to combat compositional drift. We can go to low monomer conversion. We can feed monomer as we go along. So if we're consuming monomer A faster than we're consuming monomer B, we just add more A as it goes. It's not like we hermetically seal up this polymerization and you can't touch it. So a lot of times in industry, they'll start a polymerization, then they'll feed one of the monomers that they need in order to get the same composition each time and keep the small FA and small FB the same, because the reactivity ratios don't change. Why don't the reactivity ratios change? What's that principle called? Yes. Principle of equal reactivity. So the reactivity ratios don't change. It's a function of composition or molecular weight, as far as we know. And so if the reactivity ratios don't change and we keep small FA and small FB the same, the polymer composition doesn't change. And so we can feed more, or we can starve feed. We can feed a monomer at a slow rate. So same thing doesn't happen. FA and small FB don't change. So those are some ways to think about compositional drift, and there will be clues in the questions whether we're talking about compositional drift or not, whether we're talking about low conversions and the monomer mole fractions aren't changing. All right. So in this table, it's cool. Yes. Yeah, so starve feeding is you feed a monomer at a slow rate, so it's the same rate it's being consumed. So you start with a certain small FA, like 0.6, and so you feed that monomer in slowly to keep small FA at 0.6. Yeah. All right. So in this table, it's very interesting that they tell you what monomer A and monomer B is for reactivity ratios. Sometimes they have A and B, sometimes they have other nomenclature. You just have to interpret what you're given. But the only way to figure out what the reactivity ratios are really to do experiments. People would like to be able to model it, but a lot of this data comes from experiments. So people make polymers at a small conversion. They know what the monomer feed is, and they use the copolymer equations once they figure out what the polymer composition is in order to compute the reactivity ratios. So these are usually experimental numbers, and you can see a whole range of different reactivity ratios. Styrene vinyl chloride has a huge difference in reactivity ratio. Some are pretty close to 1, although not perfect. And we have a large range of reactivity ratios. But you need to know what the reactivity ratios are to solve these sorts of problems. The one thing I'm likely not going to do is give you small FA and small FB and large FA and large FB and have you compute RA and RB. That's hard solving for those two unknowns with the two equations. And so let's leave that aside for now. But you should know in the copolymer equations, which are right here, you need to either know capital FA, capital FB, small FA, and small FB, and solve for RA and RB, or in general, you'll be given small RA, small or RB, or you'll have to look it up in the table. You'll have to figure out what small FA and small FB are, and then you'll calculate the polymer composition. That's generally how we'll do the calculations. All right. So we have a table of reactivity ratios, and in general, we can understand the order of the reactivity ratios from the stabilization of the radical. That's the minor point. It's more important that you're able to know what reactivity ratios are and use them, but this is how you make sense of some of this data. Let's see. Okay, this is just another example. Because we're talking about chain growth, copolymers, we can't forget about cationic and anionic copolymerization. And so we can compute reactivity ratios for these types of mechanisms for making polymers as well. So whether it's free radical, as we saw previously, cationic or anionic, under certain conditions, you can get different reactivity ratios. And so these are not as well studied. In general, we'll be talking about free radical polymerization when we talk about copolymers, but you want to be aware that there are different tables of reactivity ratios that you might want to check out. Okay, and this is what I just said before, because these are hard to figure out without experiments. In general, they're experimentally determined. All right, another clicker question. So we have this combination of monomers for cationic chain growth polymerization. And so where the heck is monomer A? It's up here in this table. I think this is styrene. Yeah. Styrene is monomer A. From slide 45. Great. And so our RA in this case is 33. Our RB is 0.15. And the question is, how would you describe the copolymer that would be formed under these conditions? So what's the special case where we get alternating? If you remember that from before spring break, an alternating copolymer looks like this. It's a horizontal line at FA of 0.5 is alternating. What do RA and RB have to be for alternating? Yes. 0. RA equals 0, RB equals 0. Which means if both the reactivity ratios are 0, it means that monomer A active chain N can't add monomer A, and B active chain N can't add monomer B. So cross propagation has to happen. And if you're constantly doing cross propagation, you get alternating. And so this is not RA equals 0 and RB equals 0. And so it's not alternating. What's the definition of random? What's the definition of a random copolymer? Yes.
RB equal 1.
Yep. Random is, let's say random colon. RA equal 1. RB, whoa, geez, equals 1. Said 1 and I drew 0. Great. So it's not random. You remember what ideal copolymers are too, or you can look that up. That's another special case. And so only a blocky structure is left. And so the question is, why do we get a blocky structure when RA is 33 and RB is 0.15? So let's go to our spreadsheet. RA, this is 33. This one was 0.5. Yes? 0.1. 0.15. Okay. So this is the situation. We have high RA, right? And so under all conditions, the polymer is going to be enriched in A. What happens when we use up all of monomer A? And we have some B in there. Yes?
Only B.
Only B can add. And so as long as we have some B in there, we're basically going to use up almost all of A until we're dominated by B. And then the copolymer has no choice but to use B, right? It's got no choice but to add B. Even though the reactivity ratio is very low, if there's only B in there, that's all you have left to add to the growing chain end. And that's where we get the blocky type structure from. So we're enriched in A when we start. So here's our chain. So the start. Let me not make these wavy brackets. Let me make these square brackets. Is enriched in A. And then when we run out of A, we can add only B. And so we have an A type block or an A enriched block and a B enriched block. And we might call that a blocky type structure. It's not a perfect diblock copolymer. Those are made other ways. And you'll learn about that in your future classes. But this is an important thought experiment or an important way to think through what's happening as we build polymers for given reactivity ratios and monomer mole fractions. Any questions on that? Any comments? Okay, I suggest you make your spreadsheet. You review what's going on with reactivity ratios and the copolymer equations and all the things we talked about before break, because that's what we're going to be talking about next week on the exam. We will review it. I'll have office hours. And so make sure if you're just getting back to thinking about this stuff, make sure you attend office hours, refresh your memory on the notes, look at the previous homework, then we'll go from there. Yes?
Will we need Excel for the exam or just homework?
You will not need the Excel for the exam. You won't get to use Excel for the exam. You'll just get to use your calculator and a pencil. Yeah. But this is really helpful because otherwise, if you don't make the Excel sheet, you're stuck looking at a plot like this and good luck, right? I mean, you know, that's hard to study from. It's a lot easier if you have your own sheet and you're able to figure this out. And this week, if someone reminds me, I will publish like 3 or 4 examples so you can check your sheet, but I'm not going to give you my Excel sheet because I want you to do it yourself. It takes roughly 5 minutes. Take you 10 minutes to make sure you use the graph. Make sure you use an XY scatter plot, not a line graph or something like that. And so when you go insert, can I do it here? Charts, where is it?
It's right next to your cursor.
Above and to the right. Oh, there we go. So make sure you're using XY scatter. That's how you get this type of XY plot. Don't use column. Don't use line. Line is where people really get off track here. What's the difference between line and XY scatter? Does anyone know? Line has equal X spacing. For whatever reason in Excel, this is what they call it. This was a problem when I was an undergrad. And so a line plot is like a a bar graph without the bars on the X. It's very weird. You don't want to do area, but XY scatter. Use XY scatter plots always, unless you know when to use the other. But XY scatter is what you're looking for. All right. Questions, comments? All right. I think we just have a couple more things to talk about, a couple more clicker questions, and then we'll move on here. All right, that's all review. That's all review. All right, we just talked about the case where RA and RB equals 0. You can get this from the Excel sheet, although the endpoints are a little bit funny because the formulas don't like 0 and 1 for RA and RB. But we would call this now an alternating or a perfectly alternating copolymer. And it's not blocky. There's not a few runs of A and a few runs of B. It's exactly capital FA is 0.5, which means capital FB is 0.5, which means you have one following the other. All right. Clicker question. Oh, wait, we already did that clicker question. Sorry. This is a clicker question that I wanted to do. No, we already did that. All right. There was a good clicker question that I wanted to. Oh, here we go. This is the clicker question that I wanted to do in this set of slides. All right. In the PLA quiz, whenever you took it before break or whatever, you learned that random copolymers are defined as FA equals FA. That's very interesting because there's no compositional drift under those conditions. Okay, for all values of FA, which happens when RA and RB equal 1. Thus, for random copolymerization, which statement is true? So we have our copolymer equation right here. We have the definition of the reactivity ratios. Remember, to figure out some of this stuff, you have to figure out what's going on with all the reactions. So make sure that you know which Ks these correspond to, right? What reaction is in the numerator for reactivity ratios? What reaction is KAA? A active chain end reacting with A monomer. What's in the denominator? What is KAB? What fundamental reaction? A active chain end adding a B monomer. So it's always homopropagation over heteropropagation. That's always how reactivity ratios are defined. So if RA equals 1 and RB equals 1, the rate of homopropagation for A and the rate of homopropagation for B star are equal. That would mean that KAA and KBB are equal. And so if RA is equal to 1 and RB is equal to 1, does KAA have to equal KBB mathematically? No. There's no requirement that they be equal. The rate of cross propagation is equal. Mathematically, does that have to be true if RA is 1 and RB is 1? No, because cross propagation, that's KAB and KBA. Those can be any values. Remember, what the ratio of 1 means is that the numerator is equal to the denominator, which is the rate of homopropagation equals the rate of cross propagation for both A star and B star. And that has to be true. It's very tempting to pick A or B. You're like, I know something's got to be equal. Something's equal to 1. I know, something's happening here. But remember, when these equal 1, definition of unity is that the numerator and denominator are the same. And so you're only talking about homopropagation versus cross propagation of a given species. You're not talking about what's happening with A star versus B star, because that's not in the reactivity ratios. Yes.
Hypothetically, if the rate of homophosphate isn't equal, so like if A could go to A and different enough than A to go to B, if it's not equal, how is it?
So it's the definition of a random copolymerization. So that's the tricky part, that, you know, it doesn't feel random to us. You know, it doesn't really feel like it's a random copolymerization, but they call it a random copolymerization because statistically, if RA is 1 and RB is 1, active center A could add A or B. So it's random what it picks, right? Active center B could add monomer A or monomer B equally. And so that's where randomness shows up rather than thinking about what's happening in the copolymer. So it's based on the reaction. It's just an old nomenclature. We just have to remember it. Yes?
What's the reason that compositional drift doesn't happen at all for the
Yeah, no, let's look. So for random copolymerization, we probably want to call this a random copolymerization, which leads to a random copolymer. But random copolymerization we know is special by definition. Okay, so this is what the curve looks like for a random copolymerization, right? RA equals 1, RB equals 1. And so if we put in, I'll stop this, everyone's rung in. If we put in small FA of 0.2, we get 0.2 capital FA. And so if you're winding up with the same composition in the polymer and the monomer, do you get compositional drift? No, because nothing's changing. You're taking a monomer out of the monomer solution, you're putting it in the polymer, but no composition has changed. So you can run this up to high conversion and you get exactly the same composition for all the polymers. And that's what's special about this 45-degree line. And so for 0.9, we get 0.9 in the polymer, there's no compositional drift. So when you're on the 45-degree line, whether it's azeotropic polymerization or whether it's a random copolymerization, that's the only time you're on the 45-degree line. There's no compositional drift. Yes?
In industry, are there actually true random polymerizations, or are they essentially?
They're very close. There's some reactivity ratios that are like 0.0 or 1.04 and 1.01 or something like that. Or there's 0.99, 1.05. So it's the real world. It's never perfect, but it's pretty close. So there'll be minimal compositional drift. If you look at this and let's put in 0.05, that line is pretty on the 45, right? So you're going to get a teeny little compositional drift, but not a lot. So yeah, it's worth studying. Okay, and the one that we didn't talk about was called ideal copolymerization. You want to remember what that is. And what's the definition of an ideal copolymerization? The product of the reactivity ratios is 1. So if we make that 0.1 and make this 110, why is this an ideal copolymerization? And it goes back to the definition of the reactivity ratios, that they're inverses of each other. And so remember what that nomenclature is for ideal copolymerization. It's in your notes. You can refresh your memory on that. So there's some special cases about these reactivity ratios that you really want to know and be able to recall. All right. Any questions? Any comments? All right. I've been thinking about reactivity ratios all spring break. And so, I'm ready to go. It's okay if it takes you a few days to get back, but really by Wednesday or Thursday, you want to be back to where you were on reactivity ratios. All right. Hold on. We've got one more set of notes. Not going anywhere. All right. So the last thing we're going to cover before the exam, and we have a couple days to think about this, is we're going to talk about polymer conformations. And so we started off class talking about the conformation of single carbon-carbon bonds. And so we know that we've got, I have it right here. I was going to draw it for you, but we don't have to. So you remember Newman projections of butane. That's great. So how many carbons does butane have? 4. And so we've got 1 carbon, 2, 3 carbons, because we're looking down that carbon-carbon bond, 4 carbons. That's great. So we have eclipse and staggered, or we have, I think they call it trans and gauche conformations here, depending on where the methyl groups are. And so that's conformations around one carbon single bond. But we know that polymers are a whole lot of carbon single bonds. And so we can look at this picture. This is a random walk with 4,000 equally sized steps, or this is 4,000 carbon bonds. So if we treat each of those steps in a polymer chain, or each of those bonds in a polymer chain like a step, we just write a computer program for this random walk. Now the definition of this random is kind of what we think as random, right? Could go any direction, have as a defined length. A polymer chain starts to look like this when you add up all of these different Gaussian trans conformations. And I'll bring a molecular model of a teeny little polymer, and we'll talk about this. But when we talk about carbon-carbon bond conformations, we're talking about these sorts of things. And when we add all of those up, we get chain conformations, or how a chain is coiled. And in general, we're going to draw coily chains with these smooth lines. And we know that these smooth lines are made up of individual carbon-carbon bond steps. And so we can have perhaps some order in a polymer chain. This is not super ordered, but this could be the chain could fold back on itself. And that happens in some examples, especially in a semicrystalline polymer. We can have a disordered chain or a glob, or a coil. We can have elongated, so stretched out. We could have this collapsed globule. And so what we're going to have to do in this section is to connect some of this nomenclature to sort of what we think the chain looks like. And we're going to compare and contrast these. Yes?
What's the difference between disorder and coil? You use like similar words.
Yeah, you'll use similar words. So sometimes you'll have an expanded coil. So let's say, let's just call this an expanded globule, or expanded coil. And there's good reason that we can get the coil to grow. We swell that up, or it can be collapsed. It is similar words. It's actually similar order. There's just more solvent in one than the other. And the thing that we have to remember is now when we stretch out a polymer chain in fully extended conformation, we can now figure out geometrically, because all these bonds are 109.5 for single carbon bonds, what the size of that chain is. And so we'll develop some tools to measure the sizes of these conformations and compare and contrast under different circumstances. Any questions? Yes. What's that? Oh, I have a couple more exams to grade. Just hold on tight and then I'll answer questions on that on office hours. It's coming. All right, don't forget your PLAs and homework. Come to office hours. I'll see you on Wednesday.